Hey guys, welcome back. So, I hope you have revised what we have learned in previous videos about KNN. I'll just give a quick recap of what we have learned. So, I have talked about KNN. KNN is nothing but key nearest neighbor, and then we have gone through basics of like classes. Like I have given an example of Gmail in which spam yes or no, and in that yes and no is a class. After that, we have seen how to define as a function like y equals to fx is a function in which x here is your featureization. Function can be any mathematical function or a programmatic function, and fx like f and bracket part is your classifier, and y is the predicted class label. Like if you take the example of a Gmail again, so spam yes or no. So yes and no is we will be defining here as y. If y is yes or y can be no. Alright. So after that we have seen uh, there are two phases. First one is your training phase, and your after that is your testing phase. So in your training phase we have seen like there was we have an algorithm f, and we train it using a huge training data set as xi and yi, in which we have xi values and we have yi values, which are the label. We provide that to our algorithm, and it gets trained by itself by its own intelligence. And then during the testing phase, we provide only the x part, and as it gets trained, it provides us the best prediction of the y. This is how we do that. After that, we have seen, like I have told you that by default, every vector in machine learning will be a column vector. Every vector will be a column vector here, and there are two types. Two types. First is your like vectors are of two types basically: column vector and row vector, and every vector is now defined as column vector. Then I have shown you the example of how data set looks like by giving example of salary. If Y is the salary, X is the experience and project. I hope you guys are clear with that. And there was a problem there. We have X as column vector 1 and 2, but we want to put it in matrix, we want it as row vector. So we did a transpose here, xt. So it is now like this. Okay, and then we have seen how to represent it in a matrix form like this. This is our dimension, like number of, you can say number of rows, number of columns. This is our n, number of rows. This is xi but transpose. So this is n into d, n cross d matrix, and then we have yi, this is n into 1. Okay, so now like I left the class previous video after this because it was too much of mathematics, and I've said that there is a little maths involved more, so we'll go through that. No big deal, easy thing. Okay, so let's see. So how to represent or how to define data set mathematically. Now we were defining into a matrix. Now let's define it mathematically. Let me write it down. Mathematically defining data set. Okay, so how to define that? Let me just write the equation first, and then I will be explaining you what is that. And guys, I hope you are making notes and revising after the class. You just revise it before attending the next class. It will be good. Xi, yi, I is 1 to n such that xi belongs to real number b and 1 belongs, if we take this example, let's say 0, comma 1. Okay, so this is our mathematics. This is how mathematically we define a data set in which if I want to if I want to give a definition to this equation, our data set, my data set will have xi and yi, where xi will be our input, like what we provide, like if we take the Gmail example, the words we provide to detect the spam. So this is our input. Yi will be the output, like yes or no, it is a spam or not. Yi will be the output, like from I is from 1 to n, where you have n input values. You have like n input values. You can, there can be any values, right? And this is such that the symbol belongs to such that xi belongs to real values of d dimension, and yi belongs to 0 to 1. Okay, I hope you are getting it, what I'm trying to say here. And there's one more thing. There's also one more thing. If y belongs to two outputs, like yes or no, or 0 comma 1, like 0 comma 1, or yes no, it is known as binary classification. Okay, and so if we are getting two outputs, it is known as binary classification. But if you see the example of Gmail nowadays, like recently, Gmail has uh, primary inbox, it has now promotional inbox, then social inbox, and there is a spam. So now, if you like someone is sending you a mail, there are now four possibilities to the mail. Like it can go to primary, it can go to promotional, social, or spam. So this is no longer a binary classification. I hope you understand bias for two. So this is no longer a so such uh, 1 minute. So such examples is known as multi-class classification. Okay. So if y is having two outputs, it is known as binary classification, and if it is having more than two, so you can say it as multi-class classification. All right. So now it was like uh, some of things before getting into KNN. I must tell you, not a part of like machine learning. Like it's indirectly a part of machine learning, but you should be clear with these concepts if you want to go deep into machine learning concepts, because there we will be seeing L1 norms and L2 norms. It will be helpful. Like this equation will be very useful there. Okay. So now let me just remove this, clear all this. Okay. So now get back to our KNN. Okay. So now we are again getting into KNN. Now I will be telling you what K stands for in KNN by giving you an example. Okay. Let me just change the colors here. as I'm just trying to explain a concept, giving an example. Okay, so let us say this is my negative output and blue was my positive. You can say values or positive values or negative values. Okay, so blue is my positive value and purple is my negative value. Okay, so now what exactly K is? So to define K is nothing but if I take it. Now let's say if we have a point X here, this is a new point. This is like a new data set, or you can say anything. We have new, right? So now if I want to, if my machine wants to tell that this point belongs to where, into the positive positive data set or the negative data set, where it belongs, like by looking, like we can define, we can say like by looking it comes under the positive or the blue process, so it is like it is positive. We can say that like, it is here, so it is positive. How in this case, like if k equals to 1, if k equals to 1, like it sees one nearest point, the nearest point, any one point which is very close to this new data point. So if you want to say k equals to 1, it will see only one nearest point. So let me just write it. And by looking that which is the near, okay, so blue is the nearest one. You can see it here, like the distance to this blue is this much. And if you want to say the closest purple, so let's say this. Which one is the nearest? Which neighbor is the nearest? So I hope you are getting it. Like k and n, k nearest neighbor. So if k is 1, so it will look 1 nearest neighbor. So this thing is the blue one is the nearest label, and it will, your machine will be saying that okay, this new point X belongs to positive output, like the positive data set, which is your blue one. Okay, let me just remove this. All right. Now what if I say k equals to 3? Now, as you have understood, now it will look for 3 nearest points, right? So it will say, let's say it will say take one this nearest, second this nearest, and third this nearest. Again, it will say, okay, so this is the nearest one. So it comes under blue one. But what if let me just remove this. What if our point is, wait, how to remove that? Okay, alright, so k was 3 before. And now if I want that X is here, let's say X is here, a new data set is here. Now which one is the nearest? It can be this, it can be this, it can be this. So here, if our data point, a new data point is like, if this is a situation, it will take the majority now. It will take the majority now. Like majority is blue here, okay, blue, blue, and purple. it will. So this will be your case. Like if it's like if k is 3, it is majority is blue. Now if like let's say k equals to 5, so 1, 2, 3, 4, 5. Again there are 2 purples and 3 for k. Again the majority wins, and it will your machine will say it comes to your blue data set. There is a by default data set, by default k value, which we define to give us very suitable and convenient answer that I will let you know what is the by default thing. But for now, to make you understand what is k, I'm just giving you 1, 3 and 5 examples. Basically, we take it as odd numbers, because if we take even numbers, there can be a draw, and we don't want draw here. Okay, so this is how KNN works, and K stands for this. I hope you are clear with this. Now let me give you another example. Let me just rub this. So let me give you another example. Let's say we have data data points here. Okay, so this is the case now. Now if we have a new data point here, and the value of k is 3, like we want the value of k is at 3. Now how it will say, like which is the nearest one. So this is like a condition where k and n fails, like because it is in the middle and everything is equally distant, like this is equal, or let's say this is also equal, and the third point, this is equal, or this, or anything, like everything is equal here. So here what happens, it fails, it cannot decide it belongs where, this new data set belongs to where. So here KNN fails in such cases, and there are, like if it says like this is the nearest one, if you say this is the nearest one, so like are you convinced with that this is nearest and not this? You cannot say that, like, so this is not convincing at all. So here in such cases KNN fails. There is also one more example, let me show you. I hope you have written. I mean, you can pause the video because I'm about to clear the screen. There is also one more example I want to show you where KNN fails again. Alright, so here, this is the messed up data sets, data points, messed up data points. Now if I want any data, new data point, now what you will say, which one is the nearest? Very difficult to say which one is the nearest one. Right, so in such cases, KNN completely fails. We have another thing to define that, what happens here, that we will be seeing in further classes, but I just want to say want to show you that what is KNN, what is K in that, and where it fails. KNN theory, where KNN theory fails. Okay. So now, guys, don't you think KNN is KNN is completely depending upon the distance of the data sets or data points. So the nearest the distance is the like it will decide this is the nearest one, so this will be your area where it belongs. Like it clusters and separates it to that area. So don't you think, like in short, if I say KNN depends upon distances, KNN depends upon distances. Okay, so you can make a note of all these things. Now I want to show you a very simple example, which is the distance between. Before that, I want to tell you one thing. Like that is obvious thing, but again I want to tell you that. Should I write it here? Okay. So like if I like want to say that the nearest one, or so like it is nearest to, let's say, positive, and their kn is 3. So if it's nearest to red, then it is in the red area, right? Red area. But what if k, these are the crosses you can take, and one is negative, like another one, again the red area, and this is, so that's what I'm going to tell you, that majority wins. This one is in the, let's say, another area, not red area. So like you must have good knowledge now that it belongs, majority wins. Majority, majority, majority is winning here. So if I say again, not the red area. This is just example of how it works. Alright, so now I'll just rub the screen, clear all the everything. Now I want to show you uh, one simple maths equations, and for that I guys I think you must have a good knowledge on very simple topic of maths, which is known as Pythagoras theorem, right? I'm sure everyone must be very good with this. This is the easiest, like whenever I used to solve this using a right angle triangle, I love to solve such equations. Like it's the very easy one. Still, those who are like no idea, like those who have forgot what it is, and those who are very bad with maths at this whole time, so I have to explain that again. Pythagoras theorem is nothing but when we have any triangle, basically a right angle triangle, and we have few sides, like this is the hypotenuse, base, and let's say length. So what happens? Pythagoras theorem states that if you want to find this distance h, and we know the distance of base, we know this distance, and we know L distance, but we don't know h distance. So the equation for this is h square equals to L square plus B square, and h equals to under root of L square plus B square. This is what Pythagoras theorem states. I hope everyone is now clear with this, right? Because I have to show you this, because the next thing we will be jumping is applying this same thing on one graphical calculation, that I'll show you how to derive that and everything, and it will be using this Pythagoras theorem. Okay, so I'll just rub this. Alright, so now if I want to calculate distance between 2 points on a simple graph, let's say I have a graph. and we want to find uh, distance between these 2 points. Okay, so these 2 points are nothing but your x1 and x2. So let's say we have the coordinates of x1. We have the coordinates of x1 as x11, x12. Don't get afraid, guys. This is nothing. x21, x22. These are the given coordinates to us, and we want to find the distance between these two. Like if I want to find the distance between these. This is the distance which I want to find, right? So we have x coordinate. We have the coordinates of x1 point, which is x12, and for this we have x22. This we have x11. X21. Okay, so this we have defined our coordinates. Give me a minute. Let's change the color. Okay, so now we want to find the distance d. So how, like if you used to good with maths and statistics and like basically your maths part, graphical and all, if you have such equation, how you do that? You create this, you extend these lines and you create a right angle triangle here, right? You have these distances, you have to find this. Now, don't you think this is very easy using Pythagoras theorem? We can easily find that. So, like x2 is this. From here, to here is x2, and from here to here is x1. So, don't you think this distance is x21 minus x11? This one. So, x21 minus x11. We will be getting this distance, right? So, this is this. Similarly to this is x22 minus x12. This is your this distance. So like this distance is this one. So we can write it here. This is x22 minus x12. This is your this distance. Now don't you think we have base distance? We have the length distance. Don't you think we can find the d here using the Pythagoras theorem? We can. So using Pythagoras theorem, d square equals to x21 minus x11 whole square plus x22 minus x12 whole square. This is how we can find the distance d, and if I want to shorten this up to d, so we can say d equals to under root of, I hope you know this, right? Under root, so d square will be d and so on. x21 minus x11 whole square plus x22 minus x12 whole square. Okay, so this is your Pythagoras theorem, and this is how we find d. And guys, this is also known as this d, this distance d, using Pythagoras theorem which we have got. This distance d is also known as, please make a note, Euclidean distance. Alright, so this distance is known as Euclidean distance, which we have derived from using Pythagoras theorem. I hope guys this is not that tough. This is simple graphical representation and everything is very easy, right? You can see we have the coordinate length of this. This x2 minus x1, don't get afraid with this. If you have a real graph, there will be some point like 2, 3, 2, 3 or 3, 4. Then it will be easy like 4 minus 2, it will be just 2, not x2 minus x1 and whole square. This is just to derive. I hope you guys are clear with this. Okay, so you can please make a note because Euclidean distance will be asked a lot in interviews. Even they may ask you to derive it if they have a lot of time. Basically, they'll just ask what is Euclidean distance, and you have to say using Pythagoras theorem, we find the distance, any graphical distance, we find it of the hypotenuse side, that is known as Euclidean distance. Okay, and there is one more thing I want you guys to make a note, which is a part of machine learning. This distance d can also be written as d, absolute value or the modulus of x1 minus x2, right? We are like finding the distance between x1 minus x2. This is our x1. We can say it like this. And why I'm adding 2, just leave it 2 like this. Why I'm adding here 2, I'm just denoting it to 2 because it follows a pattern, a similar pattern. So I'm just denoting it as 2. So you can just make a note of this. This distance is also written as d is absolute value of x1 minus x2, 2, or modulus of x1 minus x2. You can also say that. In a minute, I'll let you know what exactly 2 stands for. So don't worry about that. Okay? Because this d value, I'm going to define now like in a different way, a mathematical way. Same thing. This d, I'm going to show you in another thing. Give me a minute. So I'm just clearing the screen. So the d which we got there is nothing but your I1 to d, this is the dimension, x1I, x2I, the whole square to the power 1 by 2. I hope now you are getting what exactly I'm trying to say it here. It's just the Pythagoras theorem, x1 minus x2 the whole square plus x2 minus x1 the whole square and under root, like under root we define it, we can say it as 1 by 2. I know you know this much. Okay, this is nothing but I'm just representing it like this. So x1 minus x2, 2, you can say it as, guys, you can make a note as, why I'm saying 2 here is, this will be your known as L2 norm. We will be studying this into deep later on, and I will be using L2 norms and L1 norms and many other norms a lot. I will be using all these terminologies a lot, and I will be explaining when it will be the right time to explain. Okay, so this is your L2 norm. Are you like clear with this? So in short, if I am calculating my Euclidean distance, I am calculating my L2 norm. So if I am calculating Let me write it down. If I am calculating distance, I am L2 now. Okay, please make a note. This is a very important part of this. So whenever you will be calculating any Euclidean distance or anything, you are nothing but calculating your L2 now. Okay. Okay. Now let me just clear the screen again. All right, guys. So uh, now let's move to another topic. Before that, let me give you one example again. Like I hope some of my students who are right now watching this video are from US or been to US, especially in US, if they have been to Manhattan city. Like if you have been to or if you are from there, you're living there, if you're working there, you guys must have a good idea. And those who have never been to Manhattan city, they can search it on Google. Manhattan city is famous for well-defined structure. Like it is fully planned. Everything is so beautifully planned that if you see it from Google Earth or top view from any airplane or helicopter, you will see like everything is beautifully planned, somewhat like this. Like what I'm trying to say here is, these are the roads, okay? These light blue colored ones are the roads, and between them there are houses. These are the houses, planned houses, buildings, like this. These are the houses. So, and there will be a park here. So, and these are the roads. So, Manhattan city is somewhat like this. Very beautiful. You can have a look on the internet and or something. So those who are living there, I envy you, guys. Seriously, I envy you. I always wanted to go there. I just visited for a week there, and I love that place. So why I'm giving you this example, you'll get to know in a minute. So let's say you are here in Manhattan City. You are at this point, and you want to go here. You cannot go diagonally like this, right? You cannot like jump over like a Spider-Man. You cannot jump over the buildings and go diagonally like this. Since it is so planned, beautifully planned and all, you have to go like this. On this road, you have to take this road, then this road, then you have to go up, and finally you will go here. Or you can do it from this way, or if you have more time, you can even go like this. If you want to spend time, you can go like this. But I think this is the shortest distance. So from point A to point B. This is how we go in Manhattan City. Looking at this, looking at this, our machine learning developers, those who invented or this thing, they invented, by looking at this, they invented the same thing named as Manhattan distance. So this is your Manhattan distance. What I'm trying to explain, from one point, if you go like this is nothing but your Manhattan distance. All right, this is nothing but your Manhattan distance. And there is a formula as well, mathematical representation as well for this, which will be 1 to b dimension x1 I minus x2 I. That's it. That's it. This is your Manhattan distance. Like from point A, let's say point A to point B, xai minus xbi is your d, distance d. And this is known as, like, I'm not, before in my previous example equation I have written 2 here, so it was L2 norm. Here I have written nothing. It means by default it's 1 and it is L1 norm. This is your L1 norm. Alright, so this is your L1 norm. I hope you're getting the picture here, what I'm trying to explain. Okay, so like if there is only one point, there is only one point. So you can say x1. Let's say this is your L1 norm. And if you want to represent it mathematically, you can say I equals to 1 to b x1I. If you have one point, you can say it like this. I hope you are getting everything now, what I am trying to explain here. Okay, so now guys, you must have noticed one thing here regarding your Euclidean distance and Manhattan distance. There is a tricky part here to remember. A tricky part is there. Let me show you what is. Let me write the Euclidean distance here. Euclidean distance was I equals to 1 3. This was the root. Okay, so this is our Manhattan distance. This is our Manhattan distance, and this is our Euclidean distance. Have you noticed one thing? If I just remove the square and the under root, it will be your Manhattan distance, right? So that's the tricky part. If you remove square and under root from Euclidean distance, you will get Manhattan distance. So this is the good way to remember. Like you will not be doing making diagrams or anything there. Even you will not be using these equations, these complicated mathematical equations. But yeah, I have to be a good machine learning engineer. You should know everything. Especially you should be good with mathematics and statistics. Okay, so that's all maths. Like the tough maths is over now. Now everything will be so pure theoretical and so beautifully it will be. I will be trying to explain you that you will love it. Alright, so I'll just quickly recap everything what we have seen so far. Like revision is necessary, and I think you guys, like when I was a student, I know like my teacher keep on saying that are you revising, and we say no, yeah, we are doing it. So it's not like that. So I'll just revise everything from the starting in just 5 minutes. Okay, so when we started I started with machine learning, and there are machine learning problems, and I stated that machine learning problems are divided into two parts. It is Machine learning is divided into two parts. One was your supervised learning, and another one your unsupervised learning. Okay, and supervised learning is nothing but, I have given an example like teaching your child these are the blocks of houses and these are the blocks of cars. And after that, if you show any new thing to him, he'll identify, okay, so this is house and this is car. He'll identify that because we have trained him. But in unsupervised learning, we are we are doing the same. Instead, there is just one thing. We are not telling the child that this is a house and this is car. We are just keeping all the houses and cars in front of him and ask him that please separate these. Like same thing, same thing in one part, another thing in another section. So just divide it. So he'll like looking at the shape and sizes and basically observing the properties and analyzing them. He'll do that. Same thing is done in unsupervised learning. Okay, so supervised learning is was further divided into regression algorithms and classification algorithms. So regression algorithms, I have given you example like which is based on real data sets. Like I have given you my salary example like uh, 32 lakh CTC. So it is not exactly 32. It can be 31.95. It can be 32.05 or like that. So it can be like that, right? So that was regression. So predicting something output is your decimal. It is your regression algorithm. And I think I have also given you a live example of magic bricks with the housing prices. And in classification algorithm, we have like outputs are in discrete formats. Like uh, we have more than one output. Like Gmail example, if you are having a mail, there are minimum two options. Like it will go to inbox or it will go to outbox. Or I'm sorry, spam. It will go to ham or it will go to spam. So such examples are in comes under classification algorithms. Now after that, uh, in your we have started with the unsupervised learning, and inside that we have seen the first one, which is your KNN. KNN nothing but your key nearest neighbors. I have explained you what is key, what is the nearest neighbors, and how to define that. And then I've shown you example of defining function y equals to fx by giving Gmail example to make you explain y is yes or no class, and x's are the words which can be present in a mail, which defines like is it a spam or not. And after that we have seen the training phase, and then the testing phase. In training phase we provide a lot of data sets. Training data sets basically to our algorithm and train him, train the algorithm. And in testing phase, we test like what if it has learned by its own intelligence. We test to predict the future outcomes. So after that, we have seen, uh, like I have told you that there are two types of vectors, basically a column vector and row vector. And by default, every vector in machine learning is represented as column vector. You can anyhow, if you want, if it is required, you can change to row vector using transpose that we have already done. So what was next? Uh, yeah, then I have shown you how data set looks like ex, uh, experience, project, and salary, in which we have to predict salary of the employees using experience and project they have worked on. So I have given you example on that. After that, we have seen the dimensions like what is the dimension? If you say what are the dimensions, we'll see. In short, I have explained you that whatever the things comes under X are the dimensions. Okay, then we can use transpose to convert your column vector to row vector. We can use the transpose. Then mathematically, we have defined the equation of data set like dn equals to xi comma yi from I1 to n, such that xi is the real number and yi is 0 to 1. That everything is okay. You can. I I know that part is a little complicated, but if you watch my recording 2-3 times, you will have a very good understanding after 2-3 times. Trust me. So after that, we have jumped to KNN again, in which I explain you what is K, what is NNN, like the nearest neighbors and the majority, how it defines the majority and all, right? So after that, uh, like and the like there are possibilities where KNN fails. I have shown you 2 cases. There are many such cases. I'll be keep showing you as we'll be teaching. Like here KNN fails and here KNN is the best to work with. So right now I've shown you 2 examples where it fails. All right, and so basically KNN is like directly uh, dependent upon the distance. Then I have explained you Pythagoras theorem to explain you Euclidean distance. In a graph, I have shown you the Euclidean distance, how to derive the Euclidean distance and what is d. And then from Euclidean distance, so let me just create a lineage here from Pythagoras theorem. We have seen Euclidean distance. From Euclidean distance, we have seen L2 now, and then we have also seen Manhattan distance. There we have seen L1 now, and I've also given you a trick to remember how exactly it works. How to remember that if I just remove the squares and the under root from the Euclidean distance, it becomes a Manhattan distance. And guys, I'll like Manhattan is a very beautiful city, so they have given the distance as named as Manhattan distance. That's exactly how I explain how to go from one point to another in Manhattan distance. Exactly, that is happening in Manhattan distance as well. Okay, so that's all for today. In today's lecture, in this lecture, basically, tomorrow we will be continuing with KNN and some machine learning techniques, more some machine learning techniques, and then we will be jumping to linear regression, and there are many more other things to learn. So guys, I'll just request you to just have patience with me. Whatever I am teaching, just revise it, make notes, and I'm just teaching, not only teaching you to get the certificate on this. I'm teaching you so that I'm like whatever the question I've been asked during my interview, and whatever the question I've given a sheet to ask when I take the technical rounds. So I'm teaching you on basis of that, so that if you sit for any company as an AI engineer or machine learning or into deep learning, anything, so you will like already know, okay, this this was already taught, and you just simply give the right example. Even if you provide the examples which I am teaching you in class, they will be very happy. Trust me, guys. I I usually explain by giving examples, and I've been uh, like they have been this they feel very happy like when I explain in such a way, like giving examples and algorithms and analogies. Like, sir, if we do this, suppose this is a kid and these are the Lego blocks, like I've given you that example, or Gmail example. If you give such examples and explain your concept to them, so they'll get a good knowledge that okay, this guy has a deep understanding of the concept and they need that only. They don't need the bookish knowledge and everything. Alright. So I'll be giving you many more examples in the entire course of machine learning as well as on deep learning. So if you take the entire AI course, you will be having so much of examples and analogies which you can easily put during your interviews and easily crack it. Many of my students have already cracked a lot of machine learning interviews, deep learning interviews. Even there is a thing on big data, like this, it is known as CCA 175 examination. So, uh, like we are not going into big data, but I'm just explaining, giving that those analogies. It is so easy to remember things that many of my students just have already cracked CCA 175 examination. Like this is the PhD of big data. If you have this exam, if you have this certification CCA 175, basically this is a Cloudera certification. And if you have this certification, like companies in your interview, if you write in your resume that you are CCA 175 certified, they'll not even take your interview. They'll just simply take your personal round interview, like personal, what have you done so far. They'll not even go jump to your technical round and they'll just hire you. This exam is very difficult to crack, but if you remember my analogies, that's what I'm trying to say. Right now, if you might feel boring, but these analogies will help you a lot during your cracking any certification exam or interviews. Alright, so guys, I'll just request you to keep noting it down, keep revising, and I'll just wind up everything for this video. So in next video, we'll see more into KNN and machine learning terminologies and other things. Alright, so thank you so much guys. See you in the next video. Bye bye. Take care. Hey guys, welcome back. So I hope all the distances, the Euclidean and the Manhattan distance is clear in like my previous video. So today I'm going to show you the Minkowski distance, which is moreover like a generic formula to all the distances available. I'll just proceed with that. I hope guys you are revising and everything, because these are the most basic, like I'm starting with the most basic concepts which are asked in interviews for sure. Like you can make a note, like it will be asked. So whatever I'm teaching, it's like basically I'm teaching for the interview purpose so that you can easily crack any company interview or anything. Okay, just give me a minute, I'll just finish my coffee. Teaching requires a lot of coffee, you know. I'm sorry. Okay, so now let's see Minkowski distance. So this is basically nothing but a generic form of all the L1, L2, L3 norms, and like all the norms will be covered into this. Okay, so uh, it is nothing but your x1 minus x2, the distance between x1 minus x2. I'll tell you what is p here, from I equals to 1 to dimension d, x1I minus x2I. I'm sorry, p is not here. P should be up here with the power is 2 and then 1 by p. I hope, yeah, it's correct. Alright. So, guys, you can see here in the Euclidean formula, wherever there was 2, I just replace it with p. So you can see it was x1 minus x2 2, and here whole to the power 2, and there 1 by root, so 1 by 2. So this is moreover like a generic formula. So if you keep p as 2, it becomes your Euclidean distance, and if you keep it as 1, it becomes your Manhattan distance. So this is moreover like a generic formula, and there are, you can say it L1 norm and L2 norm, you can get even many other norms you can derive from this equation. All right. So now if you see, like uh, basically there are, like in machine learning, there are like hundreds of distances available, like we can find hundreds of distance available. And in my experience, and in wherever I have worked with projects and in companies, I have learned around, let's say, 10 to 15 the most important and most widely used distances I have learned. So like whatever I have learned, I will be covering most of them in this entire session of machine learning. And I have learned like 10 to 15 distances which are like widely used, so I will be covering that. Most importantly, L1, L2, and L3, these are widely used. So these three we will be working a lot on these threes. Okay, so now there comes one more thing named as Hamming distance. Hamming distance, guys, those who are from computer science background, in your, I think in your first semester or first year, there was a chapter named as, like when I was studying, there was a chapter named as computer architecture. If you are from that and if you studied the computer architecture, you must have heard about this Hamming distance word. It is the easiest of the entire machine learning. This distance is the easiest, and I'll make it more easy. Trust me, in like few minutes, this is the easiest one. So basically, it is used where you want uh, where like it is used where x1 and x2 are Boolean vectors like 0 or 1. So I'll just write it first. Use when where x1, x2 are Boolean vectors like uh, let's say 0 or 1. So they are used there. So I'll just give one example. Let's use this one. Suppose we have x1 as uh, let's say I have x1 as 0, 1, 1, 0, 1, 0, 0, and so on. I have a series of this, okay, and I have x2 as 1, 0, 1, 0, 1, 0, 1, and so on. So my Hamming distance here, Hamming distance x1 and x2 here is the locations where your binary vector differs. Like wherever the binary vector differs will be your Hamming distance. Let me just explain you how. See, 0 and 1 are, they are not same. These are not same. These are same. 1 and 1 are same. 0 and 0 are same. 1 and 1 are same. 0 and 0 are same. 0 and 1 are not same. So you can see now. Here your Hamming distance for x1 and x2 equals to 1, 2, 3. So your Hamming distance is 3. That's it. Easy, right? So this is how easy it is. So like it is why, like if you are using Hamming, like you must, there must be a question like where to use Hamming distance. So if you have a binary, like if you have binary vectors, then you should go for Hamming distance. This is the simplest one and very straightforward. Okay, so this is your Hamming distance. Also, I'll just like you guys can note it down. I'm just rubbing it. So I I'll just tell you one example where I have worked with. Like when I was in a company and there was a project, it was a medical domain project in which there was, I'll just give you example to simplify. This is not the real example which I'm showing, but I'm just simplifying it so that you can understand easily. So I was working with a medical domain project in which, let's say there was a person X1, not X1, there was a person and these are its DNA strands. Like in medical domain, let's say A, B, G, H, M, N, C, Z, D, and these are like, let's say these are the DNA strand. I'm not saying, I'm not into medical, I have no idea about that. We just have to work. So this is B, A, G, C, M, N, D, Z, F, and so on. Let's say these are the genes or DNA strands or whatever you want to say. These are like for a person. Now I want to find, like I want to predict how it will work. So basically I'm just showing you uh, how this Hamming distance works here. So find out wherever there are different, like you have to see wherever all the locations where your binary vectors differ. It is differing. It is different here, here, here. So guys, tell me, what is my Hamming distance for x1 and x2 here? If you are saying 5, very good. Like you can give yourself a treat. So you got it, right? Hamming distance, you are clear with Hamming distance here. So I hope you are clear with all the distances now. So now let me introduce you to another topic. You can pause the video and you can make notes in your own words and everything. Now let's switch to another topic, which is kind of important topic. Okay, so our next topic is cosine similarity and cosine distance. So guys, whatever we have learned in KNN so far, do you think there is a relation between similarity and distance, be it a positive relation or negative distance, negative relation? So don't you think if the similarity, if the distance is more, similarity will be less? Like we have seen the examples of that blue and green crosses. If the new point comes and it is close, like the distance is less to a particular area, similarity will be more, right? So less the distance, more the similarity. So can I write it in this way? Similarity is inversely proportional to distance, right? So the more the similarity, lesser will be the distance, or the lesser the similarity, more will be the distance, or vice versa. Yeah, right, guys? Are you like getting what I'm trying to say here? Okay. All right. So let me define the same thing mathematically now. I think I should clear the screen here. Okay, so let me define this mathematically. So guys, can I write it in a way? Before that, let me give you an example so that you can understand that. You guys must have heard or worked on probability questions when you are in your 12th or preparing for your engineering exams. Right, so basically by default, we take probability, total probability as 1. Total probability, we always take it as 1. Like we find it from 1. It is always 1, right? So let's say there is an outcome, like I want to say like the probability of this outcome is like for yes, the probability is 0.7 and total probability is always 1. So for no, it will be obviously 0.3, right? So how we do that? So it is like if for probability yes, it is 0.7. So it is like total probability minus probability of no. You can find it like in this way. If I want to write it in own words, so it can be for yes equals to total probability minus no. We can write in this way, right? And total probability is always 1. So why I am explaining this, you'll get to know in a minute. Okay, so let's keep it. Oh my god. All right. So now let me define the same thing in the previous cosine formula. Let me just write it first. 1 minus cos similarity. I'm just writing similarity as sim of x1 comma x2 equals to cos of distance. I'm writing distance as this and x1 comma x2. Okay, so now I hope you are getting like 1 is our like you can take it as 1 it as a total probability minus similarity equals to cos of distance of x and y. Obviously we are talking about x1 and y1, so x and x. All right, so this is how we do. Now let me just show you something related to this. If my cos distance is like, let's say it is 0, let me say like let me first write it down. If cos similarity x1 comma x2 equals to 1, if this is equals to 1, don't you think don't you think 2 points are very similar to each other, right? I hope you are getting it. Like they are very similar and the distance is 0. And if cos distance of x1 and x2 is equals to 1, it means 2 points are very dissimilar. So I hope you are getting it what I'm trying to say here. If I want to explain you, let me just try to explain what I'm saying here is if I take, like, if I want cos similarity as 1, if I want this, like cos similarity as 1, don't you think it will only happen when cos distance, when this becomes 0? When this becomes 0, you can just shift this minus here and 1 will be here and it will be. So distance is 0, it means it is coinciding a point, so the similarity is 100%. Are you getting it? And similarly, if I put this as 0, this thing as 0, so so the distance, like similarity is 0, so distance will be 1, like it is equals to 1, and they are very dissimilar now. I hope you are getting it now, right? Okay, you should make a point on this. It is important. I'll explain you in a graph as well now. Alright, so I'll just rub this. Okay, so now let's see the same thing on a graph to get a better understanding now. So I have a graph. I have 2 points. Okay, let's change the color. I have 1 point x1. I have 1 point x2. And this is our origin, which is basically 0, 0. So x1, basically we want to find the distance between x1 and x2, which is this distance. We want to find this. So before like using Knn and Euclidean formulas, we find it using that formula, which is you guys feel very difficult. But here in cosine similarity rule, what happens is we do not find this distance. We don't find the distance here. Instead, we see the angle here. We see the angle here and we decide whether they are similar or not. So if I want to write it here, if I want to write this, cos similarity equals to cos theta. So angle, say theta is nothing but your angle between x and x1 and x2, right? So cos similarity is cos theta. Now guys, tell me one thing. If theta is 0, like theta is 0, these two lines will be coinciding, right? Then similarity will be 1. Okay, and when what I said, when similarity is 1, whenever the similarity is 1, these points are very similar. So that's what, like if this is 0, these lines will be coinciding, like this line will be above the, like this will be coinciding and it will be very similar, right? I hope you are getting it now. All right, so I'll just show you one more example here. Zero comma 0, we have 2 points. One is your x1, one is your x2. Let's connect these lines. All right, so now guys, tell me one thing. We have a point, let's say vector point x3 somewhere here. We have a point x3 somewhere here. This is a point x3, not x2, it's x3. Okay, so what will be the similarity between x1, x2 and x3? What is the similarity between x2 and x3 here? Think. You can pause the video and think, and if you are right with me, like I'll take a take an excellent from my side. Okay, so suppose this is our theta angle between x1 and x2 and x1 and x3. Basically, what is the similarity between x2 and x3? So uh, if you are saying theta is equals to 0, if theta is equals to 0, don't you think cos similarity equals to, which is your cos theta here, equals to 1? So if cos similarity equals to 1, 2 points are very similar. So like in this diagram I've shown you, if theta is 0, so this will be very similar. I hope you are getting what I'm trying to say now. Now guys, tell me one thing. If I ask you the similarity between x2 and x3 and between x1 and x2, like uh, which one is more similar, x1 and x2, or x1 or x2 or x3? Let me write it down. X1 and x2 are more similar, or x2 and x3? Tell me that. So if you are saying x2 and x3 are similar or more similar, you are right. Now you have the idea why they are, because theta is 0 and cos of 0 is 1 and cos 0 is 1, so it will be similar. Okay, I hope you are getting what I'm saying now. Okay, so let's move. I'll just erase this. Alright guys, so there is one more concept now. X1, let's take it x2 here. This is x1, this is our theta. Okay, so this is our theta and x1 and x2. Now guys, this is the concept which I am explaining. This is from our 12th standard, 11th and 12th standard, which is our unit vectors and dot products. So you must have seen, like, I'm assuming this distance from origin to x1 and x2 are like x1 and x2 are unit vectors. What does that mean? The unit length, the length of this is 1. So that means this is our unit vectors. So if I take cos theta here, cos theta equals to x1 dot product x2. You must have known about dot product, right? So x1 dot x2 upon distance of x1, I'm taking as L2 norm here, distance of x2. So this is nothing but your L2 norm. I'm just taking as length as L2 norm. I'm finding it through L2 norm. Okay, so this is x1 mod and x2 mod. So this is the formula for cos theta if we are working with dot product and unit vectors. Okay, so you are getting this L2 norm using your Euclidean distance formula. Now, since these are the unit vectors means like x1 and x2 are unit vectors. which means x1 equals to x2 equals to 0. I'm sorry, not 0, equals to 1. Okay, so unit vector unit is 1, right? So these are 0. So if we keep the length x1 length and x2 length as 1, this formula will become cos theta equals to x1 dot x2. So this was just a concept which will be used further. I'm just revising what we have learned from class 12th, 11th, 12th. Alright, so this is how we work with unit vectors and dot products. And if you have, like, you must be having doubt with L2 norms, and L2 norm is nothing but your distance, which is x1. We are taking it as unit vector to just simplify it, and the distance we can calculate through Euclidean distance, and I have already mentioned that Euclidean distance is nothing but your L2 norm, and Manhattan distance is your L1 norm. And we will be seeing L3 norms as well in further lectures. You will be seeing that. So till here, I hope everything is clear. Make a note. I'll just move to another topic, and that topic is not required in your machine learning, but some of my students were saying that they have simply asked this topic. It was a mathematical topic, but in their interviews, some like 2 3 of my students have asked, like, said that, sir, they have asked this. Somehow they managed to solve it, but since it's being asked, so I think I should let you know. That's not tough, like only 3 4 lines of topic. I'll just tell you right away. Before that, everything is clear up to this? No doubts? Alright. So I'll just erase it, okay? So our next topic, which is asked in interviews, I have seen people asking, interviews are asking this, is relation Alright, so this is what the relation between Euclidean and cosine distance. So they may, like, when you are sitting in an interview, face-to-face interview round, so they'll just provide you one paper and they'll say, okay, so you know the relationship between Euclidean and cosine distance. If they ask you, you don't have to derive everything, because deriving that will take like 20 minutes or 15 minutes, and they don't, both of you guys don't have that much time. So you just have to give the what is the relation exactly between Euclidean and cosine distance, which I'll show you now. Okay, and for this, make sure whenever this question is asked, make sure x1 and x2 are unit vectors. Only then there is a relationship between Euclidean and cosine distance. You can make a asterisk here or a star point that this relationship is only applicable when x1 and x2 are unit vectors. Unit vectors is nothing but their length is 1 unit. Alright, so what it is? So Euclidean distance, I'm denoting it as ED. Euclidean distance of x1 and x2 whole square equals to 2 of twice of 1 minus cos theta. This is the relationship between Euclidean distance and cosine distance. So cos theta, let us simplify this. 2 minus 2a multiplied by bracket of 1 minus cos of similarity, as we have already seen. You can also write it as 2 of cos of distance. So guys, I hope you are getting a picture, a relationship between Euclidean and cosine distance now. As we have already seen, 1 minus cos similarity equals to cos distance. So I have just replaced that, keeping the 2 outside the bracket. And this is how we do. Okay. This is only just this line. Even if you just say this, if you just say if it is asked by an interviewer, if you just say this, only this, you are selected. Or any of this, or if you write all the three, then that's more than good, right? So I hope this is clear. So it's been asked. So that is why I'm telling you. Alright, so let's jump to a new concept now. A basic concept now of Knn. Now we are again entering to Knn, and enough of maths for some time. Okay, so now let's see. I'm just clearing it. Now let's see how we measure the effectiveness of Knn. Like our Knn, our model which we create. Like you remember our algorithm function f which we used to create. How effective it will be. Like how good it is. So let's see that now. Okay. So let me name the topic as effectiveness of Knn model. Okay, so I'm just creating a table here. Okay, so guys, you remember the thing y equals to fx, in which we have already seen the salary part. Here it was like project and years of experience, and here it was salary, where we used to predict salary, and it was the yi part, and these two are the xi part. You remember that? I'll use the same example but with different values. Here let's say I'm taking age, here I'm taking gender, here I'm saying will purchase or not. This is just an example, guys. Dataset doesn't at all look like this. There are more columns and n number of rows, and this is just to explain you. Okay, so let's say I have uh, I have a guy of age 20, gender is male, and he will purchase. There is some item that we are just finding out he will purchase or not. So let's say yes, he will purchase. Then I have another of 25 age, and let's say she is a female and she'll purchase yes. Then I have 30 years old, say male, he'll purchase, no, he will not purchase. Then let's say 32, female, yes. 40, male, no. 42 female. Yes. So this is a simple data set of we have to figure out whether like if a new member enters, let's say a new member enters 30 comma f, so she will purchase the item, yes or no. We have to find that. Before that, this is like prediction. Before that, there will be a training phase and then the testing phase, right? So we have to see that. If you are revising my previous videos and your notes, you should not be having any problems now here. So what happens, we just this like as we have already studied in previous example, we take it as yi as a function and these two are xi, right? So dimension is 2, everything is clear, right? Okay, so we create a model here, uh, an algorithm f to predict whether she will purchase or not. But guys, don't you think uh, like if I create with these values, like we'll get a right answer or not? Like the values are very less and we cannot like it cannot predict like anything, like it can depends. So for me, it's not a good model for like if you're working in, let's say, a company or a production system, a huge production system. This model will not work. Like only with the example of age and gender, I'm just keeping training the algorithm and finding out whether it is a yes or no. It is not and like it is not a good approach. So there is a problem. This is the problem, right? So like I'm not confident enough that this model will give accurate predictions or not. Like I have created this algorithm, this model, and even I'm not confident enough. So this is the problem. Now, like, so how we can determine whether the model we are creating is a good model or a bad model? Like, I created this model. Like, that is why I have named this as effectiveness. How effective this model is. I have created this model, but whenever I have trained it, but whenever a new person enters with 30 age and female, and I have to predict, I'm not even confident. Like, okay, I think this model will fail or this model will not give the accuracy. The prediction will not be good. So this shouldn't happen. So what I will do, let me just rub some of the things here. All right. So okay. So instead of taking all the values, like creating a model of all the values, what I'm doing, I'm instead of taking all the entire data set, I'm just taking a section of it. Let's say there are 1, 2, 3, 4, 5, 6. Suppose that there are 6 values. In real cases, there will be 6,000 or 6 lakh values. But let's say in our example, there are 6 values. So I'm taking 4 values of it, and I'm not taking these 2 values. Okay, so I'll train my algorithm. I'll train my model. I'll train my model with these 4 values only. Okay, and I'm not even touching these 2 values. I'm not even touching these 2 values. So I'm just training from these 2 values. So I'll call it as training data set. So this is my training data set, and since I'm not even touching these values, I'll call it as unseen data set or test data set. I'll call it this. Okay, so these two values I'm calling as unseen data set or test data set. So what I'm doing it here is, now see, I'm training with these four values. Okay, I'm training it. Now, before directly giving it a new value of 30f to predict whether it's yes or no, what I'm saying, I already have these values, right? I have these values, like I have the x of these, I have the x and I have the y. Like I have x as 40 comma m, and for this I have y as no. So I know y, but this, since I have named it as test dataset, I can test only with x. Like if I pass only x to it, and if I pass this, and if I get this output, same output, don't you think our algorithm is working correctly now? Because it's giving the right answer. Similarly, I can uh, try it with another x, which is my 42f, and I know the value is, I know the result is y, but I'll just pass this again, will not pass the y value, and if I get this thing, then we'll say okay, our algorithm is working fine. So then finally, like if it say our accuracy is good, like let's say our accuracy is more than 90%, that I'll let you know how we calculate the accuracy. So now we can finally pass this value. Now, since we are confident now, okay, whatever the algorithm we have created, whatever the model we have created, it's giving the right answer, and we have even cross-checked it. Even we have cross-checked it. Now, if we pass it, we are little confident, more than like before. We are confident, like okay, now whatever the answer it will give, there is a high probability that it will be accurate, yes or no. I hope you are getting what I'm trying to explain it here. This is not a real data set. This is just I created one data set to explain you how we do, or how we check the effectiveness of KNN. Are you getting it? I hope you are. All right. So now let's say I need to rub this. So I'm just rubbing it. Okay. Now let's say I have um, 10,000 data sets or data points. 10,000 data points, in which, like in my previous example, there are 6 values, out of which 4 I have used for training, named as training dataset, and 2 I have used for testing, so that we can cross check. Similarly, if I have 10,000, like 6 values won't be there when you're working on real projects. Suppose we have 10,000 data sets or data points. Out of that, I have like provided 9,000 for uh, for training. I have like 9,000 values. I have used it as training set, and remaining 1,000 for testing or comparison. Testing or comparison. All right. So, like out of these 1,000 values, like don't look on these 9,000 values right now. Okay. Now just focus on the testing comparison dataset, 1,000 values, which we are using for testing. Let's say out of these 1,000, 900 900 values or the 900 outcomes were correct and 100 were wrong. So, like how to calculate accuracy now? So we can say accuracy is 90% here. I hope you know how to calculate the percentage. Accuracy is 90%. How 90%? That 900 upon 1000 into 100. So we can say that accuracy is 90% and it is a very good accuracy. So basically, how good is my model? We calculate using accuracy, how good my model is. So here I can say that 90% is my model, 90% accurate is my model here. My model of 10,000 data sets, when I have used 9,000 for training, 1,000 for testing, in which I am getting 90% accuracy. So I can say the model which I have created is 90% accurate and it is very good. So this is how we create models here, and we find the accuracy of our model if it's good or not. And guys, these one more thing, this suppose we have 10,000 data points, and if you have to choose 9,000, we don't choose it like from starting 9,000 or from bottom 9,000 values. 9,000 values are taken randomly, okay, and the rest over will be your test comparison values. Data we usually take it as randomly. So this is how we do the comparison and accuracy. Now let me erase this. I want to give the generic representation of everything we have studied in this accuracy part. So generic representation. Okay, so we have a data set which was 10,000 in my previous example. We have a, let's denote it as Dn, and I'm using, in that I'm using 9,000, so I'm using some part of Dn for training and some part I'm using it for testing. So guys, I'll just denote training as N1 and N2, and let me denote it as. So don't you think N equals to N1 plus N2 always? Like this was 10,000 in my previous example, it will be equals to 9,000 plus 1,000, right? So this is my generic equation. N is equals to N1 plus N2 here. Now minimum requirement, if you have a huge data set like 10,000 or into thousands, if you have data set in thousands or maybe hundreds, let's take it hundreds, N1 should be approximately equals to 70% of the data set, and remaining is obviously it should be 30% approximately. What I'm trying to say is that if you have 10,000 values, you can, for training, you can take randomly, you can take 7,000, at least 7,000 you should take for your testing, and then automatically 3,000 will be there for for training, and 3,000 will be for testing. This is how, if we have a huge data set. So like basically, more the accuracy, better is our model. So if we increase the accuracy, the better will be our model. Like here you do everything right, but don't you think like if you have just have 10, let's say in worst condition you have 10 data sets. So here if you take 70%, 7 for testing and 3 for 7 for training and 3 for testing, the output will be very bad accurate. So here what I will suggest you, like it's up to you. Like if you'll be working with machine learning projects in companies, then you'll get to know like if such values, you should have accuracy, high accuracy. So you will take 9 for training and 1 for testing. So this is how you do. But if you have hundreds or more than hundreds, like thousands, you at least should take 70%. I have seen people taking even 90%, and N1 as 90%, and N2 is 10%. I have seen that. I work on basically 80 to 85%, but by default, and like you should take at least 70%, not less than that. Accuracy will be very bad if you take less than that. And this thing is decided. This thing is decided by data scientists. What to take as and what to take and what to not. All right. So this is how we do everything here. So I'll just quickly revise what we have seen in this today's lecture. So we have gone first. We have seen Minkowski distance, which was nothing but your LP norm, in which you just have to add p instead of 2 in Euclidean formula, and whenever like whatever the value you put, like if you put the value of p as 1, you will be getting Manhattan distance. If you put the value of 2, you will be getting Euclidean distance. So this is how you work on. Then we have seen the Hamming distance, which is the easiest distance to calculate, and I have shown you how to do that. We just take whatever there are in binary vectors, whatever there is are not matching, we count those values, and that is our distance. Okay, and after that we have seen cosine similarity and cosine distance, in which similarity we have seen that it is inversely proportional to distance. The more the similarity, lesser will be the distance, and lesser the similarity, more will be the distance. After that, we have defined it mathematically using the probability type of statement, like 1 minus cos similarity equals to cos distance. Then we have seen like if the cos similarity is 1, it is very similar, and if the cos distance is 1, it is not similar at all. After that, I have shown you graphical representation, how to calculate x1 and x2. Yeah, I think I should just a concept of maths again for cosine value. Just a cosine graph, quick graph. Let me just show you. Guys, I hope you know what is pi by 2, pi, 3 pi by 2, 2 pi. This is graphical representation of basically our sine and cos. We used to do that in our school. So if you are working with sine, cos, so our graph somewhat goes like this. Change the color. Please forgive me for such a bad graph, but I hope you are getting. So basically, this is 90 degrees, this is 180 degrees, 270 degrees, and 360 degrees. Right? So this is what we use. This is cosine graph. This is how it goes. So cos 0 is 1, cos 90 is 0, cos 180 is minus 1, and this is how we do that. This will be useful in for a few further lectures. So this is how I'm just trying to explain one topic here. Okay, then when we have seen unit vectors and dot product, in which we finally got a result of cos theta equals to x1 dot x2. Then we have seen the relationship between Euclidean distance and cosine distance, in which it is been these days asked by interviewers. So you just have to say Euclidean distance of x1 and x2 the whole square equals to 2 into 1 minus cos theta. Cos theta can be you can rename it as cos similarity, or 1 minus cos similarity, you can put it as cos 2 into cos distance. After that, I have shown you the example of how to find out or measure the effectiveness of KNN by giving that example of data set. First, how we train our data set, and with the given values which we already have, we just cross check it if our model is predicting the right values or not. And that prediction is based on our accuracy, which I've shown you how to find the accuracy. The more the accuracy, the stronger the model is. Okay, we cannot go and directly train our data set and we'll just say, okay, now just provide the simple new data sets and let's whatever the prediction it will make, we are okay with that. We cannot do that. We just first train it and we test it. Okay, and minimum requirement is we should take at least 70% for training and 30% for testing. So that's all for today in this lecture. Tomorrow we will be working more on ML tech terminologies and technologies, and hardly one lecture of KNN is left. KNN will be over in next video. So after that we will be working on linear regression and ML technologies, and there are many other things. So we will be working on that in my next videos. So I hope you are noting each and everything down and revising it, because this is a theoretical part. Theoretical part, if you are not revising and revising it, it will be gone in few weeks or months. So, and trust me, if you want to enter ML and if you are sitting in front of your interviewer, they'll ask you theoretical part only. So I hope you are revising everything. All right, guys. So let's end this video here. You can switch to next video for another lecture for the continuation of ML. All right. So thank you for watching this video. Bye bye. Take care.